Well, hello and welcome to today's lecture. We are on chapter 14. We're going to start 14.4, then we're going to cover 14.5, and after the lecture, we're going to have our quiz. Okay, 14.4 is about linearization. Why we need linearization or linear approximation? Very well. For example, in machine learning or deep learning, we use different algorithms. Suppose you have a three-dimensional object and you're trying to actually project that three-dimensional object and construct a two-dimensional model for that three-dimensional object. So, in augmented reality, I already posted a link, augmented reality for GeoGebra. You can download the app. You can actually take pictures of three-dimensional objects, and that app actually uses linearization to project that three-dimensional object into a two-dimensional format, then create a three-dimensional object back for you. So one of the most important applications of linear approximation or linearization is in image processing. Okay, so what is linearization or linear approximation? Let's write down the definition. We are on page 1. The definition is as follows. So suppose we have a function in two free variables. Let z equals to f of x and y is a function in two free variables. So, equation of tangent plane at point P with coordinates x sub 0, y sub 0, z sub 0 to the surface of the function is as follows. So here you have z minus z sub 0 equals to. So what are we going to do? We're going to use partial derivatives that we learned last time. Is equal to the partial derivative of f with respect to x at this point, x sub 0, y sub 0, times x minus x sub 0 plus the partial derivative of f with respect to y at that point, x sub 0, y sub 0 times y minus y sub 0. So let me just erase this, shift them a little bit here. X sub 0, y sub 0, x minus x sub 0, plus f of y, partial derivative of f with respect to y at the point x sub 0, y sub 0 times y minus y sub 0. So the equation is very familiar to us. Where have we seen this equation before? Remember that in two-dimensional world, equation of tangent line to a graph of a function, for a function like y equals to f of x, the equation of tangent line at point like a and b or x sub 0, y sub 0 is as follows. You have y equals to mx plus b. What is m? M is equal to the derivative of the function, at that number. So we just generalize the idea from equation of tangent line to actually form equation of tangent plane. Since you have a plane, you're going to have equation of a plane which is tangent to the surface or the graph of function in two free variables. Let us go over one example to feel comfortable about constructing equation of tangent plane. So we are working with planes. The question says, let me change my marker. Example. Find equation of tangent plane to the function what is our function? Z equals to 2x squared plus y squared at point 1, 1, and 3. So let us write down equation of this tangent plane. Then we use our website to actually visualize the tangent plane to this function. So to write equation of tangent plane, we're going to follow the formula that we just learned. Z minus Z sub 0 equals to the derivative of the function with respect to variable x at that point times x minus x sub 0 plus the derivative of the function with respect to variable y at that point, given point, y minus y sub 0. So let's take a look at the point here. 1 is the first coordinate, 1 is the second coordinate, and 3 is the third coordinate, Z sub 0. So this guy is given, this is 3, this guy is given 1, this is given 1, and you know that these points are 1 and 1. 1 and 1. Okay, we need the partial derivative of f with respect to x. So f of x is 4x. Here you have 4x. So let me, for now, just write down x. And then here you have x minus 1 plus partial derivative of f with respect to y, 2y at this point, and y minus 1. And you have z minus 3 equal to, okay, 4x when x is 1 is going to be just 4. So 4, and it doesn't have any y in it, so we're just going to forget about y. It's going to be 4 times y times x minus 1 plus, and here you don't have any x, you only have y, so y is equal to 1. You get 2 times 1, y minus 1. We're done with calculus part, the rest is algebra. We have z minus 3 equals to 4x minus 4 plus 2y minus 2, or z is equal to 4x plus 2y minus 6 plus 3 minus 3. Equation of tangent at this point. So if we change the point, we get a different equation. Tangent plane at 1, 1, and 3. Very well, let's try to visualize what's going on here. So our first function is z equals to, let me just erase these, 2x squared plus y squared. So 2x squared plus y squared. And the second one is your tangent plane, 4x plus 2y minus 3. Well, here we go. Let me just rotate this one a little bit so you can actually see the tangent plane. This is your plane, which is tangent. So this is the plane, which is tangent to the surface at 1, 1, and 3. We can just change the dimensions here. So you see this plane, which is tangent to the surface. Again, this is exactly the generalization of tangent line from a 2-dimensional space to tangent plane into 3-dimensional space. We are on page 2. So we say that a function like f is differentiable if you take the partial derivatives, those limit definitions. You take the partial derivatives of the function, those partial derivatives, those limits, both of them exist, and both of them are continuous on open disks. A function like f of x and y is differentiable if f of x and f of y partial derivatives of the function with respect to x, with respect to y, so these are partial derivatives. Both the limit definition exists, f of x and f of y, the partial derivatives are continuous on an open disk. So, if a function is differentiable, how do we define the differentiation of that function? The differential of function f is defined as, so you need partial derivatives of the function f of x with the direction in the direction of x-axis, so partial derivative of f with respect to x in the direction of x-axis plus partial derivative of f with respect to y in the direction of y-axis. This is the differential or differentiation of your function. You need directions in the direction of x-axis, in the direction of y-axis. For example, question says, example, So suppose your function is z equals to x squared plus 3xy minus y squared. Question says find dz. What's the differentiation or what's the differential of this function? Very well. First, let us check to see if this is a function that actually satisfies the conditions that we talked about. So first of all, you need to find the partial derivative of f with respect to x, which is 2x plus 3y. So as you can see, this is just a plane. It is continuous everywhere. It is a plane and continuous everywhere. So we're good with first partial derivative. What about the second partial derivative? It is going to be 3x minus 2y. Again, you have a plane. It is a plane with the same argument. It is continuous everywhere. So these two conditions are met. So now we can form the differential of this function. dz is equal to the partial derivative of function with respect to x, 2x plus 3y in the direction of x-axis plus 3x minus 2y in the direction of y-axis. One checkpoint for you. Show that the following function, f of x and y, which is equal to 5x plus 4y squared, is differentiable. Then find dz or df. So what's the differentiation of the function? What is dz?
I got dz equals 5x dx plus 8y dy.
So 5, which is the partial.
5x.
5.
Oh, I'm so sorry. Just 5.
5, very good. 5.
dx.
dx, excellent. Plus
8y dy.
Excellent. Thank you very much. So this is the differential of the function. How about your tangent plane? What do you have? Z is equal to
10x plus 8y minus 14.
the rest of the class. What do you have? If I plug in 2, if I plug in 1, I can get my Z.
All right, minus 4.
Minus 4, okay.
Yeah.
So let us solve these. You're done with the differentiation. Let us solve how to get equation of tangent plane. So to get to the equation of tangent plane, we're following the formula that we just learned. It is z minus z sub 0 equals to f of x at the given coordinate times x minus x sub 0 plus f of y, x sub 0, y sub 0, y minus y sub 0. So what is z sub 0? You have a point that has the first and second coordinate. the third coordinate is not given. So since you have z equals to 5x plus 4y squared, your z is equal to 5 times 2 plus 4 times 1 squared. So z is equal to 10 plus 4, so z is equal to 14. This is actually your third coordinate, 2, 1, and 14. So you have all the information. You just need to write down the equation of the tangent. Z minus 14 equals to f of x. You know that that guy is 5 times x minus x sub 0, which is 2, plus f of y is 8y. It is 8. What is your y? 1 times y minus 1. So here you have z minus 14, 5x minus 10, plus 8y minus 8. So z is equal to 5x plus 8y. Here you have negative 18, and here you have plus 14, negative. Equation of tangent. Let us start 14.5. So let us write down the formulas first. So 14.5 chain rule, and then we're going to talk about implicit differentiation. So we are on page 1. Very well. So suppose you have a function in 2 variables. Let z be a function in 2 variables. And also, you're introducing a new variable like t, such that x and y are dependent on that new variable. Also, suppose that x and y are both dependent on a new variable like time, temperature, or any variable like t. So suppose x is equals to gt and y is equal to ht. So z is actually a function of t. So here's a question. How do you take the derivative of function z with respect to t? What is the derivative of z with respect to t? Well, since x and y, both of them are functions of t, we have to include these in the formula that we are introducing for the partial derivative or just the derivative of function z with respect to t. That's how they define it. They say that, hey, the derivative of z with respect to t is equal to. So here you are taking the derivative, partial derivative of z with respect to x, then taking the partial derivative of x with respect to t, plus, and we have to add the second one as well, taking the derivative of z with respect to y, y with respect to t. So here we have partial derivative of z or f with respect to x, and partial derivative of x with respect to t, plus partial derivative of z with respect to y times partial derivative of y with respect to t. We have 2 variables, x and y, and both of them are dependent on t. So we have to include all derivatives when we are taking the derivative of function z with respect to this new variable. So here's another question for you. Question. What if x and y are dependent on two variables instead of just one variable, like t and s. How about that? How do you take the derivative of function z? So suppose your x is g of t and s, and y is h of t comma s. What would be the derivative of the function with respect to t, and what would be the derivative of function with respect to s? So instead of having just one derivative, we're going to have two derivatives, one with respect to t and the other one with respect to s. In this case, we need to find two derivatives. One with respect to t and the other one with respect to s. Can I generalize the idea? Of course. Suppose now I'm having three different variables, t, s, and let's say l. How do you take the derivative? So since you have three variables, you have to write three different differentiations. So as I mentioned before, function z is dependent on x and y, and x and y are defined as two other functions. So I expect you to ask, can I substitute these two functions here and just write the function in terms of one variable t? Of course. Sometimes it's much more easier to do the substitution instead of writing the formula like this. Let me show you. Example. Question says, let the function be defined as f of x, y, and z equals to xy plus z. And what do you have? You have x equals to s squared. So x is a function depends on s, and y is dependent on s and t multiplied. And also you have your z, which is equal to t squared. Z as a variable is a function which is dependent on t squared. Question says, find the derivatives of f with respect to t and s. Well, here you can say that first I'm going to substitute all of these here and write function as a function of s and t. I want to get rid of x, y, and z. We can substitute x, y, z into the function. What do you get? You get f of s and t, t and s equals to, here you have x times y. X is s squared, y is st plus z, which is t squared. So your function st is s cubed, t plus t squared. From a function in three variables, we reduce the dimension in a function with two variables. So we just reduce the function into two variables. So what is f of s? F of s is 3s squared t. What is f of y? F of y, or f of t, sorry, not y, ts cubed plus 2. We're done. There you go. In checkpoint on page 1, you have the following function. So here you have z given as x squared y plus 3x, let's see, y to the 4, and x is given as sine 2t, sine function, and y is cosine, cosine t. Question says, find dz dt, find the derivative of the function with respect to t, then t is equal to 0. So what do you have? dz over dt. dz over dx, dx over, let's use the partial format since we're taking the partial derivatives. dz dx times dx dt plus dz dy dt. So what is dz over dx? What's the derivative of z with respect to x? This is equal to 2xy times partial derivative of x with respect to t. It gives you 2 cosine 2t plus dz dy. Here you get x squared. Oh, I missed this part. Let me just write it here for you. Okay, we have a plus and we have x here. I forgot about the second part. Okay, 2xy plus 3y to the 4th. And here this guy is 2 cosine 2t plus, then dz dy, we have these two. So let me write it here for you. We get x squared plus 12xy cubed times the derivative of y with respect to t is negative sine t. Okay, since it asks to find the derivative with respect to t, we cannot have x and y in the final answer, in the final equation. So we're going to do the substitution. And we write this as dz dt equals to. So 2xy, we have 2 sine 2t and y, which is cosine t, plus 3y to the 4th. Y to the 4th, and inside you have cosine to the 4th of t times 2 cosine 2t plus x squared, which is sine 2t. So you have sine squared 2t plus 12x y to the 3rd. X is sine 2t and cosine to the 3rd of t times, so there's no subtraction here, sine t. Well, here you can distribute these into parentheses and try to find if you have common factor, you can try to simplify the expression. dz dt is equal to, so let's distribute this into parentheses. You get 4 sine 2t cosine 2t and cosine t plus 3 cosine to the 4th t cosine 2t minus, let's distribute this into parentheses, And note that we have subtraction, so we have to change this sign as well. Minus sine t, sine squared 2t, minus 12 sine t, sine 2t, and cosine to the third of t. Okay, seems like that's it. I'll leave it as it is. This is the derivative of the function with respect to variable t. And it must be written in t. We cannot leave it including x and y because you took the derivative with respect to t. Okay, and the final step, as you mentioned, thank you, is to plug in 0 to find the rate of change z with respect to t when t is equal to 0. So it's not that hard. The rate of change of z with respect to t when t is equal to 0 is equal to. So this guy is going to be 0. This is going to be 6. This is going to be 0. So here minus 0 and another 0. So the rate of change is positive. It means that it's going to be an increasing function. Okay, what else? We have implicit differentiation. So I'm going to erase this part of the board. So on page 2, we have more checkpoints. We're going to move on to page 3 and talk about implicit differentiation. So before talking about implicit differentiation in 2 free variables, let's get back to Calc 1A or elementary calculus. Recall, if you have a function like y equals to x squared plus 2, and the question says, hey, find the derivative of this function, you say that, okay, f prime is equal to 2x. And if you have a function written this way, implicitly, x squared plus y squared equal to 0, and they say, hey, now find the derivative of the function, you take the derivative of this function implicitly, or you follow the formula y of x equals to minus the derivative of this function with respect to x divided by the derivative of the function with respect to y, which is equal to minus the derivative of the function with respect to x is 2x divided by the derivative of the function with respect to y, d2y. Okay, so this is the derivative of your function, y of x minus x divided by y. We have the exact same concept when it comes to functions in 2 variables. It's actually just an example of a function in 2 variables. Why is that? This is x squared plus y squared equal to 0. Here you have 2 free variables and you're done. Well, suppose you have a function written implicitly. Implicit differentiation. So suppose your function is given as let f of x, y, and z is equal to 0. Like what? Like this function that I'm giving to you. For example, I'm going to write down two examples for you. Here, like x cubed plus y cubed minus 6xy equal to 0, or another example for you, x squared plus y squared. Here we have minus 2x cubed, sorry, minus 2z squared plus, this is z squared plus 12x minus 8z minus 4 equal to 0. So these functions are written implicitly. It means that it's very hard to isolate x on one side or y on one side and write the function in terms of the second variable. Again, the same here. It's very hard to isolate just x, just y, just z on one side and write the function in terms of two other variables. So how do we take the derivative of the function? Well, to take the derivative of the function with respect to x, it is equal to minus the derivative of f with respect to x divided by the derivative of function f with respect to z. To take the derivative of the function, one of the variables, I'm talking about z as a function of x and y, with respect to y, this is equal to minus the derivative of the expression that you have with respect to y divided by the derivative of the expression with respect to z. So if you have just two variables, you can take the implicit differentiation this way. So you can write y of x equals to minus f of x divided by f of y. So zx, zy, yx. So you can write it this way. So here you don't have any z. You can find the derivative of y with respect to x. So here you have the derivative of y with respect to x, which is minus. This is your expression. The derivative with respect to x is 3x squared. This is 0 minus 6y divided by the derivative with respect to y. This is 0. Then you have 3y squared minus, with respect to y, 6x. I expect you to ask, what if the question says, find the derivative of x with respect to y? What is this guy? You have to just put it. Minus 3y squared minus 6x divided by 3x squared minus 6y. Of course, you can just factor out 3 and cancel out 3. It makes it prettier, but this is just the derivative. Here, you can take the derivative of the function with respect to two variables, partial derivative of z with respect to x, which is negative. So we're taking the expression, the derivative of the expression with respect to x. It means that the rest of the variables are constants. So with respect to x, you get 2x. This is 0, this is 0, this is 12. And the partial derivative with respect to z, this is 0, this is 0. Here you get negative 4z, and here you have negative x. We can factor out 2, simplify this. Partial derivative of z with respect to y is equal to minus. Here we take the derivative with respect to y, which is 2y. We don't have any y here, and the partial derivative with respect to z is going to be the same. As I mentioned, you can simplify both of these. So negative 4z minus a. Here you get x plus 6 divided by 2z cos 4. I distributed this negative sign here as well, and here you get 5 divided by 2z cos